Hello everyone. Today we will explore how geostrophic currents shape our oceans, driving circulation and impacting marine ecosystems in ways you might not expect. Winds cause surface water to converge and diverge, forming sea level hills and valleys, which create horizontal pressure gradients. Water flows from high to low pressure, countered by the Coriolis force until geostrophic equilibrium is reached, where the pressure gradient balances the Coriolis force. Currents in this balance, called geostrophic currents, are tropical of ocean currents. Ocean circulation is driven by wind stress and buoyancy, with wind-driven currents near the surface and thermohaline circulation reaching the seafloor. The Coriolis force is an apparent force caused by Earth's rotation, which causes moving objects to appear deflected. For example, if a ball is rolled in a straight line on a rotating surface, its path curves to an observer on that surface. On Earth, this deflection makes wind and ocean currents curve to the right from the North Pole towards the equator and to the left from the South Pole, shaping global weather patterns and ocean circulation. Next, I will specifically introduce the formula for geostrophic flow. The first equation illustrates the true change in frame velocity, represents the difference in final velocities in the rotating frame. The left-hand side is the Coriolis term, which arises because of the rotation rate. The right-hand side represents the centrifugal force, another force we experience due to the rotation. The second equation is the true change in coordinate velocity in a rotating reference frame. The left term represents the rate of change in velocity in a non-rotating frame. The right term represents the Coriolis effect, and it accounts for deflections due to rotation. Combining these two equations, we see that the third equation includes the Coriolis force, the centrifugal force, and the direct change in velocity, providing a complete description of how an object's velocity changes in a rotating frame. In recent years, academic research on geostrophic flow and its impact on Earth has primarily focused on how geostrophic flow affects marine ecosystems in the context of climate change, with numerous studies conducted across various sea regions. For example, this article examines the impact of climate warming on geostrophic flow by exploring future changes in upwelling along the California current system under climate change, focusing on the combined effects of Ackermann transport and geostrophic currents. Comparing future and historical simulation data, it highlights spatial temporal upwelling changes. Figure 1 shows monthly variations in vertical upwelling transport and wind stress, revealing enhanced upwelling in high latitude regions during spring and summer. Figure 2 analyzes upwelling components, indicating that geostrophic currents, particularly at low latitudes, sometimes surpass Ackermann transport, especially under future scenarios. This paper utilized CREO-SAT-2 satellite altimetry data to analyze sea surface height anomalies and geostrophic currents in the Arctic Ocean from 2011 to 2020. Figure 1 shows key Arctic regions, including the continental shelf and deep basins, main surface currents, and observation points for data verification. Results reveal the seasonal and regional distribution of SSHA, with long-track analysis highlighting seasonal flow characteristics. Figure 2 shows weekly data differences between ice cover and ice-free areas, with coastal currents accelerating and SSHA peaking in winter, especially on the continental shelf. I hope this video has helped you understand ocean circulation basics and the role of geostrophic currents, including their formation, formulas, and recent research. Thank you for watching.